Okay, we are on chapter 26, current and resistance. Let's share the PowerPoint and get started. They start off with a substation. I'm sure you probably drive past one, uh, or you've seen them. You see them along the road. It's our distribution centers for in urban areas, suburban areas, on how to get electricity into your house. Most of your outlets are 120 volts, but it actually comes into your house at 240 volts. That's why your dryer will have a different plug on it than your regular 120 volt uh, plug that you have in your everyday appliances, because it runs on 200. At least most electric dryers run on 240 volts. So they're showing you a substation, and then they're looking at water. And why are they showing you water? Because there's a lot of analogies between water flow and electric flow. The water flow in a hose or a pipe, water flows because of pressure differences, and current flows because of voltage differences. And so they're showing you Niagara Falls, and Niagara Falls flows at a rate between 1,400 cubic meters per second and 2,800 cubic meters per second. Well, we have a flow rate for current. It's called amperes, and it's 1 coulomb per second. We'll get to that. And there's so I'll be making analogies quite often to water flow and pipes. Water flow through a pipe when we're talking about resistance, but we'll get to that. And so here's a description of electric current. The direction of the current is the direction in which positive charges flow when free to do so. Now, most of the time when we're talking about conductors, it's actually the electrons that flow. And so we talk about, so if an electron moves from one position to another, it leaves what we call a hole. And so positive charge is kind of what we call hole flow. But actual current is electrons flowing through the conductor matrix. It was just a convention that started, and once we realized, well, it's really electrons that flow and not protons, well, it just stuck, and we live with it, and it works fine. So the average current is the delta Q over delta T. How many charges cross through the area A in delta T time. And for instantaneous current, it's is equal to dq dt. And once again, the unit, SI unit for current is the ampere, and it's 1 coulomb per second. Now let's look at the microscopic model of current, and we have this volume. If you have A times delta X, the area times this delta X, you get a cylindrical volume of probably something like a conductor, and you have n number of mobile charge carriers per unit volume. That's the charge carrier density. N is the charge carrier density. So the total charge, Q, is the number of charge carriers, the charge carrier density, times that volume, area times delta X, times Q, the charge on each electron or each proton. And here they're showing you protons. So that's the total charge. Now, the delta X, going all the way back to chapter 2, delta X is equal to velocity times delta T. The old distance equals rate times time. Well, rate is your velocity and time is your delta T, and that's the distance. So that's the equivalent equation. And the charge density times the area times velocity delta t times q. Like now, let's divide both sides by delta q by delta t, and we get the average velocity delta q over delta t is equal to nq vd Now, the reason they have vd, that's the drift velocity. We're going to introduce that in a little bit. The v drift. So the average current is the number of the number of charge carriers per volume, or the charge carrier density times the charge, individual charge, times the drift velocity times the area. Now, this is drift velocity. The random motion of the charge carriers is modified by the field, and they have a drift velocity opposite the direction of the electric field. So if you just have a conductor, there will be random motion depending on the kinetic energy of the based on the temperature, the kinetic energy of the molecules, the atoms inside your conductor. You're going to have just random drift in all sorts of directions. But if you apply an electric field, the drift velocity is going to be the electrons are going to, they're still going to bounce around, but their tendency is going to be to drift in the direction opposite the electric field. Now, you know, some people have the idea, well, if you flip a light switch, boom, the electrons move at the speed of light. No, they don't. The electric field moves at the speed of light. It's generated almost instantaneously, but the electrons move very slowly. I think there's even a problem of how long it takes electrons to move down a particular wire, and the answer is in years. Don't think of drift velocity of anything moving at the speed of light. It just kind of moves gradually. But when you have a lot of them moving gradually, that can make for 1 amp current. Okay, now here we have a quick quiz. Consider the positive and negative charges of equal magnitude moving horizontally through the 4 regions shown in the figure. Rank the current in these 4 regions from highest to lowest. Well, let's start with A. We've got 3 positive particles moving in this direction and 2 positive particles moving in this direction. Well, the 2 positive particles moving in this direction is equivalent to 2 positive particles moving in that direction. So total, we have, it's the equivalent of 5 particles moving to the right. The 3 positive and the 2 negative, that adds up to 5, the equivalent of 5 particles moving to the right. Now let's look at B. How many particles do you see? Well, they just show you 4 particles moving to the left, and so it is what it is. 4 particles. So in A we have 5, in B we have 4, and in C what do we have? Well, we have 2 going to the right, 2 positives going to the right, and 2 negatives going to the left. Well, the 2 negatives is equivalent to 2 positives going in to the right. So we have 4. It's the equivalent of 4 positives going to the right. And in D, all we show is 2 negative particles moving to the right, and that's equivalent of 2 particles moving to the 2 positive particles moving to the left. So we have 5, 4, 4, and 2. So basically, they're already lined up. A is greater than B. B and C are equal. They're both they're in opposite directions. 4 particles to the left in B, and 4 particles to the right in C. And then D has the smallest amount, the equivalent of 2 particles to the left. Now, they didn't ask you about direction. They just asked you rank the current from highest to lowest. So it's 5, 4, 4, 2. And I think that, yes, that ends our discussion on section 1. We'll end here, and we'll pick it up with the next section, resistance.